Hi, this is Module 4, entitled Relations and Functions. Let me share with you this PowerPoint presentation as we discuss the topics relations and functions. So relations, by definition, let A and B be sets. A relation R from A to B is a subset of A cross B. Given an ordered pair, XY, in A cross B, X is related to Y by R, written XRY, if and only if XY is in R. The set A is called the domain of R, and the set B is called its codomain. So the notation for the relation may be written symbolically as follows: ARY, which means that the ordered pair XY is an element of R, and X not related to Y or not RY, which means that X and the ordered pair X and Y is not an element of R. Let's take an example for that. First, let's take this example 1. Let A be equal to the set 0, 1, 2, and B equal to 0, 1, and define a relation R from A to B as follows. Given any ordered pair XY, element of A cross B, the ordered pair XY is an element of R, means that X plus, that's X plus Y over 2 is an integer. So let's clarify, guys, that this is X plus Y. So this question is, state explicitly which ordered pairs are A cross B and which are in R, and is 1R0, 2R0, and 2R1 a relation? What are the domain and the codomain of R? So when we talk about that problem, we see this as a solution. First, state explicitly which ordered pairs are A cross B and which are in R. So A cross B is simply the Cartesian product of A and B. So 0 and 0, 0 and 1, 1 and 0, 1 and 1, 2 and 0, and 2 and 1. So these are the A cross B. Now, is 0, 0 part of R? 0 plus Y over 2 is an integer. So we could say that 0, 0 belongs in R. How about 0, 1? Well, 0 plus 1 is 1. 1 over 2 is not an integer. So 0, 1 is not present here in R. Same with 1, 0. However, 1, 1, 1 plus 1 over 2 is 2 over 2, which is 1. Which means that 1, 1 is part of R. 2, 0 is also part of R. 2 plus 0 over 2 is 1. But 2, 1 is not an element of R because 2 plus 1 is 3. 3 over 2 is 1 and 1/2, which is no longer an integer. So as we could see, the elements ordered pair 0, 0, 1, 1, and 2, 0 are all part of R, or elements of R. And these elements are also elements of A cross B. Now, is 1R0 satisfies the defining condition for R? As I have explained earlier, 1 plus 0 is 1 over 2, that's 1/2. In short, 1R0 does not satisfy the defining condition of R. The same with 2R1. However, 2R0 satisfies the condition of R. Henceforth, 2, 0, as you can see here, is an element of the set R. Now, what are the domains and the codomains of R? The domains of R are as follows: 0, 1, 2. If we refer back to the set notation of, or the roster set of set R, we could see that that is the first element of all the ordered pairs, or the first term. in the three ordered pairs. That is the domain of R. While the codomain of R are the second terms of all the ordered pairs of R. So in short, the domain would always comes from set A. And the codomain would always come from set B. All elements of set A that satisfies the defining condition of R, or could satisfy the defining condition of R given a proper pair in set B, is its domain, and all elements of B that could satisfy the defining condition of R given a proper pair in set A belongs to the codomain of R. Now, suppose R is a relation from set A to set B. The arrow diagram shows R is to obtain as follows. Number 1 represents the element of A as point in one region and the elements of B as point in another region. For each x and for each x in Y and Y in B, draw an arrow from X to Y if and only if X is related to Y by R. In short, we only draw an arrow from X to Y if XRY is true, or if the ordered pair XY is an element of the set R. So let's take, for example, this problem. Let A be equal to 1, 2, 3, and B equal to 1, 3, 5. And define the relation S and T from A to B as follows. For all XY, ordered pair XY, element of A cross B. Ordered pair XY is an element of S, means that X is less than Y, or the relation T, which means T is equal to this set that contains ordered pair 2, 1 and 2, 5. So let us draw a diagram for S and T. So these are the diagram for S and T. For instance, in set A, all the elements are written down. In set B, all its elements are also being written down. Now, we connect only an arrow if the element in A is related to the element in B. So as we could see, 1 is related to 3 and 5 because it satisfies this condition that X is less than Y. 1 is less than 3 and 1 is less than 5. However, 1 and 1 are not connected because they do not satisfy this defining or the definition of the relation of S. In the same way, 2 is related to 3 and 5, but not to 1, because 2 is greater than 1. But 2 is less than 3 and 5, which satisfies S once again. And lastly, 3 is only related to 5 and not to 3 to 1, because 3 is no longer less than 3 and less than 1. In this diagram, we could see that T is a relation. And T defines such relation that the element in A is related in B only if it satisfies this set, which means that 2 is related to 1 and 2 is related to 5. 1 is not related to any of the elements of B because, as we can see, that element of A is related to B by this definition. Same with 3 by this definition. So what are the domain of relation S? We could say that the domain of relation S is 1, 2, and 3, while its codomain is 3 and 5. In relation T, we could say that the domain is 2 and the codomain is 1 and 5. Let's check our progress. Let A be equal to 2, 3, 4, and B is equal to 2, 6, 8. And let R be the divides relation from A to B for all XY element of A cross B. X is related to Y if and only if, let's just say Y is divisible by X. Y is divisible by x, which means that if we divide y by x, there is no remainder. So let me try to answer this one. We draw a circle and we write the elements of A, which is 2, 3, and 4. And we draw another circle, 2, 6, and 8. Now, is 2 divisible by 2? Yes. So we draw an arrow. Is 6 divisible by 2? Yes. Is 8 divisible by 2? Yes. How about 2? Is 2 divisible by 3? No. So we don't draw an arrow. Is 6 divisible by 3? Yes. So we draw an arrow. Is 8 divisible by 3? No. Is 2 divisible by 4? No. Is 6 divisible by 4? No. Is 8 divisible by 4? Yes. So we draw again an arrow. And that is how we draw an arrow diagram for R. So now let's move onwards. I believe that if you have time, kindly do this problem in order for you to have practice. Now, there's a special kind of relation that we could say, we could call as function. A function f from set A to set B is a relation with domain A and codomain B that satisfies the following two properties. First, every element x in A, there is an element y in B, such that x and y is an element of f. Again, every element of x in A, which means all the values of A must be used. Next, for all elements of x in A and y and z in B, if x and y is an element of f and x and z is an element of f, then y is equal to z. If A and B are sets and f is a function from A to B, then given elements x and A, the unique elements in B that is related to x by f is denoted by f of x, or this one, which is read as f of x. Let's take this example. Let A be equal to 2, 4, 6 and B equal to 1, 3, 5. Which of the relations R, S, and T defined below are functions from A to B? We say that relation R or any relation is a function if each x has a unique pair in y, or each element that is in A has a unique element pair in y. In R, we could say that R is not a function but a relation because an element in A, which is 4, has two pairs in element B, or in set B, which is 1 and 3. So in layman's term, actually, simply saying that in order for a relation to be a function, it should be that for every A, there's only one B, unique B. If there's two elements in B that is paired in A, then that's not a function. But if we say that there's two elements in A that is paired in the same element in B, that is still a function. Like here in letter C, there's two elements in A, 4 and 6, that is related to one element in B, that is 1. But it does not violate the function rule, because the function rule states that for every x in A, there should only be one x in B, and not the other way around, or one y in B, and not the other way around. So 4 is related to 1, and 6 is related to 1. Still, this is a function. Now, how about relation S? For all xy, element of A cross B, xy is an element of S, which means that y is equal to x plus 1. We could say that this is a function because for every element x, there's always a unique y, a single unique y for every element s. X, if x is 1, then y is 2. If x is 2, then y is 3. If x is 4, then y is 5. So in short, there's only one y for every x. Now, we now look into functions, or like a function machine, in which we input the value of x and it provides us its value in y, or its pair, which is f of x. For instance, the squaring function f from r to r is defined by the formula f of x is equal to x squared for all real numbers x, which means that every time I input a real value x here in this squaring function, I get a f of x, a value for y, which is the square of everything I put in this squaring function. Like this successor function that we have seen earlier. Every value of n that I enter in this successor function, it outputs a value, unique value, which is n plus 1. The same is also true for this function from q to z, which is defined by the fixed formula hr is equal to 2. Every time I input a value r, that value is paired with 2. I input 1, it's paired with 2. I input 4, it's paired with 2. I input 10, it's paired with 2. Is it still a function? Yes, it is still a function. Because, again, there is a unique, for every r, there is only one y, or h of r. There's only one h of r. That's 2 for every r. 1 is not paired with any other value. 1 is only paired with 2. So is 3, so is 4, and so is 5. So these are actually examples of the function that we have seen earlier. For example, number 1, find the f of 1, negative 1. So I input 1 here in this function, negative 1 rather. So it gives me negative 1 squared. In the same manner, I input here 999 in this n here. I replaced it with 999. It gives me 1,000. 999 plus 1. So now we have this equality of functions. They say that f equals g, written as f equals g if and only if f of x is equal to g of x for all x in A. For example, f is a relation r to r, and g is also a relation from real to reals. Real numbers to real numbers, and g is also a relation from real numbers to real numbers by the following formula. First, f of x is absolute value of x for all x element of r. And g of x is x squared square root of for all x element of r. Thus, f of g, f is equal to g squared, g, question mark? The answer is yes. Because any value I replace here for x, like for example, f of 20, that's absolute value of 20, that's 20. G of 20 is 20 squared, square root, which is also 20. If I input here negative 2, the absolute value of negative 2 is 2. The square root of 2 squared is still 2. So f is equal to g. How about question number 2? A is a relation from, is a function from real numbers to real numbers, and B is also a function from real numbers to real numbers with the following formulas. Ax equal to x squared for all x element of r. and dx equal to negative x squared for all x element of R. Indeed, 9 squared is still 81, and negative 9 squared is still 81. If we square this one, the negative value cancels out. So f of x is still equal to, a of x still equal to b of x. So a and b are equal to functions. So this is the end of our lecture for functions. And if you have questions, kindly note it down. And let's discuss that on our synchronous meeting next time.